All right, so this chapter, chapter 2, is going to review the chemistry of life. So in this first section, chapter 2.1, the chemistry of life, we're going to talk about from atoms to molecules. So you should be able to distinguish between atoms and elements, describe the structure of an atom, define isotope and summarize its application in medicine and biology, and then distinguish between ionic and covalent bonds. So in this first section, we're going to talk about from atoms to molecules. Matter is everything on Earth is going to be comprised of matter. The air we breathe, the water we drink, everything that takes up space and has mass is matter. And all matter exists in one of four states, either a solid, liquid, gas, or plasma. All matter, both living and non-living, is going to be composed of basic substances that we call elements. Elements are just substances that cannot be broken down into simpler substances by ordinary chemical means, meaning that they're going to be composed of only one type of atom. So each element has its own unique chemical properties such as density, solubility, melting point, and reactivity. So again, with elements, what we mean is you just can't break it down any further. So whether you're talking about a single atom of gold or a brick of gold, it's all going to be the single element of gold, as long as it's pure. Same with carbon. If you have a brick of carbon, doesn't matter if you break that brick in half. It doesn't matter if you break that brick all the way down to the tiniest microscopic level. At all points, it is the element of carbon. So it's when we cannot break it down any further into a different substance. There are 92 elements that are naturally occurring. However, only 6 elements make up 95% of the body weight of all organisms. Specifically, humans are made up of over 90% are going to be made up of just 4 elements: carbon, nitrogen, oxygen, and hydrogen. The body weight of all organisms are made up of 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So here we're going to start talking about atoms. John Dalton is the 19th century English scientist who developed what we know today as the atomic theory. This states that all elements are made up of tiny particles known as atoms. If it helps you to remember, the word atom comes from the Greek word atomnos, which just means uncut or indivisible. So an atom is going to be the smallest part of an element that retains the physicals and displays the physical properties of that element. So an atom and an element are going to share their same name, and they're going to be annotated with a 1 or 2 letter symbol. So for example, what we have here is hydrogen over here on this small portion of the periodic table. This isn't the whole periodic table, just a small piece of it. But this over here is going to be the atomic symbol for hydrogen. It's a single letter. Over here we have helium, denoted with an He. Now this is not an abbreviation. You don't need to put a period after it if you're using it in a sentence or anything like that. It's considered a symbol. So a helium is going to be represented by 2 letters, He. Carbon is going to be represented by the letter C. That's the atomic symbol for carbon. N is the atomic symbol for nitrogen, so on and so forth. So here's just a portion of the periodic table showing how that works. Like I said, the word atom is Greek terminology for uncut or indivisible. It's the smallest part of an element that still displays the properties of that element. Whether you have a brick of gold or a single atom of gold, gold is always going to react in the same way to the same influences. It'll have the same melting point, whether we're dealing with a ginormous block or a tiny little, atom. It has the same melting point, density, all of those different physical properties. Although the atom cannot be broken down by ordinary chemical means, it is going to be composed of several smaller building blocks. These are what we call subatomic particles. These particles are what give the unique characteristics and features to the atoms. They vary in location, charge, and mass. And these are the things that I would like you to know. I would like you to know for all of our different subatomic particles, our neutrons, protons, and electrons, I want you to know where they are located and what their charges are. So for an example, these are the 3 types of subatomic particles that we're going to focus on in class. Like I said, they're differentiated by their charge, mass, and location. So the very first that we're going to discuss is going to be the protons. Protons are located inside of the nucleus. These are going to be positively charged. They're going to have a mass of relatively 1, and they are ultimately going to be responsible for a lot of the unique characteristics of the element. So for example, gold is gold because it has 79 protons in its nucleus. If we were to take one of those protons away, and so we only have 78 protons, suddenly what we have is not gold, it is platinum. We've completely changed the identity of the atom if we add or subtract protons. Carbon is carbon because it has 6 protons packed into its nucleus. If it had 7, it would suddenly be nitrogen. So the number of protons is absolutely essential to all of the characteristics that make an element unique. Neutrons are going to be our next subatomic particle that we're going to discuss. These are also found inside of the nucleus. So we have our protons and our neutrons right inside of this nucleus. Neutrons are neutrally charged, meaning they have no charge, but they also have a mass of 1. Variations in the number of neutrons doesn't change the element, but it can change the radioactivity of the element. This can lead to radioactive isotopes, which we will cover in just a moment, so hang on to that. If we change the protons, we change the identity of the atom as a whole. If we change the neutrons, we can change its radioactivity. Now, electrons are going to be the third subatomic element. These are subatomic structure. Subatomic particle. These are, however, not found inside of the nucleus. These are going to be found orbiting around the outside of the nucleus in little, what we refer to as energy shells. These are also going to be negatively charged, and their mass is so small that it is negligible for our calculations. So for all intents and purposes, electrons have no mass, but they do have a negative charge. Now this is going to help balance out the positive charges inside of the nucleus. So for example, in our carbon atom, we have 6 protons, so we have 6 positive charges. We also are going to have 6 electrons, or 6 negative charges, to help balance out that atom. Now if we take away an electron, we're going to be taking away one of those charges. If we add an electron, we're going to be adding a charge. We're going to be adding a negative charge. And so it's going to be very important when we change the number of electrons. So protons give the atom its properties and characteristics. Protons give it its identity. Neutrons, or changing the number of neutrons, can give the atom its radioactivity. Electrons, or those charges found around the outside of the atom, are going to change its chemical activity, and that's going to play a huge role when we start discussing chemical bonding. So it's important to note that the majority of the atom is empty space. I know that we have it drawn kind of all close like this, but I just want to point out that if this hydrogen atom right here were drawn the size of a football field, the nucleus would be the size of a gumball in the center of the field, and the electrons would be whizzing around in these microscopic particles up around in the upper stands. So these hydrogen atoms, or these atoms, are going to be primarily large empty space. These models are only going to be approximations of where the electrons might be found. Because they are constantly moving, we don't know exactly where they are at all times, but through mathematical calculations, we can determine approximately where their location is. So, the next thing we want to talk about is the periodic table and how we can or some of the terminology that's going to help us discuss atoms and atomic structure. Like we said, each element is going to be represented by 1 or 2 letters to give it its unique atomic symbol. So for example, down here we have carbon, and its atomic symbol is going to be a C. Now the atomic number is going to equal the number of protons in each atom of the element. All atoms of the same element have the same number of protons in the nucleus. Every atom of carbon has 6 protons. This is what gives the element its unique properties. Generally, atoms are going to be considered electrically neutral, meaning that there's going to be an equal number of protons as electrons. So if we have 6 positive charges like we do in carbon, we will have 6 negative charges. So that's our atomic number. Now the mass number is a little bit different. The mass number is going to be equal to the sum of the number of protons and neutrons that are found in the atom's nucleus. The atomic mass is going to be the average AMU for all isotopes of that atom, and it's going to be approximately equal to the mass number. Typically, when we're looking at an atomic symbol, the atomic number is going to be written as a subscript in the lower left-hand side of the atomic symbol. The mass number is going to be written above as a superscript. Now, since the mass number is going to be the total number of protons and neutrons, we can determine how many neutrons are in an atom if we have the mass number and the atomic number. So here we have the total number of protons and neutrons. Here we have the total number of protons. If we take 12, subtract 6, so if we have 12 protons and neutrons, we subtract 6 protons, we're left with 6 neutrons. This is how we can determine how many neutrons are found inside of an atom. Isotopes are going to be atoms of the same element that differ in the number of neutrons. So therefore they have different atomic masses. Still the same atom, but they have different atomic masses. The official atomic mass you see listed on the periodic table is the average mass for all the isotopes of that atom. Since the majority of carbon is carbon-12, meaning that we have 6 protons and 6 neutrons, we're going to see that the atomic mass is much closer to 12 than it is to 13 and 14. Now, like I said, there are different versions of carbon that exist. There is such a thing as carbon-13. Carbon-13 has 6 protons. We still have 6 protons. However, we have an atomic mass of 13, meaning that 13 minus 6, we have 7 neutrons. So carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons found inside of it. So this is how we can use atomic mass to determine the number of protons and neutrons. Now, the reason why we care about this is because isotopes that have, have varying numbers of neutrons can make the element unstable or radioactive, meaning that it's going to decay spontaneously. When it does this, it's going to give off energy in the form of rays and subatomic particles. So, for example, carbon-14 will decay over time to become nitrogen-14, which is going to be the stable isotope of nitrogen. So, carbon over time will actually decay by taking on an additional proton. The radiation that's given off by radioactive isotopes can be detected in a variety of ways and used to date objects from the past, create images, and to trace the movement of substances in the body. So low levels of radiation. In the case of low levels of radiation, we're going to see that the chemical behavior of a radioactive isotope is essentially the same as that of a stable isotope. So you can put a small amount of radioactive isotope into a sample and it becomes a tracer where you can detect molecular changes. So for example, we could use radioactive glucose and inject it into the body. And it's going to be used in the same way that normal glucose would. The body's going to take it up, the body's going to use it. But what we can do is use that energy that it gives off to trace or to locate that glucose in the body and determine what is happening inside the body. So this is often going to be used to image body tissues and organs. And we're going to actually pause right here, and we're going to pick up with a portion of the periodic table and its elements in just a moment.